Welcome to AP Chemistry at Hononegah High School. I'm Brian Brown, and today we'll be looking at PES, photoelectron spectroscopy. Now, special thank you for the ideas and the worksheet I modified from Dr. Dina Leggett. She's an AP chemistry teacher out in Texas. And when I was looking at this idea, because it's a brand new idea for AP, I really began my work by looking at some of the stuff that she developed, and everything that I've got here is really modified off of her work. And the doctor part, she is actually she received her doctorate from NI University, so she's a homegrown talent that's out teaching AP chemistry, and I have a lot of respect for some of the stuff she does. What you're looking at here is an example of a PES machine. Now, this one is a little bit different than what we're going to be talking about here, because this is really dealing for using photoelectron spectroscopy for the surface of metals. But if you replace the surface of metals with a stream of gas being hit by high ionizing radiation, high energy radiation, it's fundamentally the exact same idea. And here is a quick picture about what's happening inside there. You've got some sort of high energy source, typically X-rays or ultraviolet. In this case, they're showing X-rays. And you're going to bounce it around and channel it against, in this case, our sample would be the surface of a piece of metal. Now, we can also replace components in here with a stream of gaseous particles. And now when our high energy ionizing radiation comes in and hits our particle, instead of hitting the surface of a metal, we're going to be knocking ions out of a gaseous element. And fundamentally what happens is when a photoelectron is emitted, it goes through our lens here, gets channeled around, and comes down and hits our detector. And this multi-channel detector's main job is to really calculate one thing. What is the kinetic energy of the photoelectron that was emitted? Now, if you remember, this is related to Einstein's photoelectric effect. It's the same idea. This is really just a device used to measure photoelectrons. If you hit the surface of some metals and we're using that to a slightly different degree here, but if you hit the surface of some metals with um, uh, a photon of high enough energy, some minimum frequency or minimum energy, you'll emit a photoelectron. Below that, no photoelectron gets emitted. Above that, the photoelectron comes out with higher kinetic energy. Well, it's a similar type of principle here, but instead of releasing just a single photoelectron, what we're using is this high energy radiation to knock out and measure the kinetic energy of all of the different electrons inside an element. And so the main thing here is really the multi-channel detector at the end. What it's going to be doing is measuring the kinetic energy of the photoelectron that comes out. And in a second, I'll explain how we use that. But first, let's go back up and take a look at what's happening here. This component, remember, is our energy component. That is Planck's equation, H times nu. The X would be whatever particle it is, whatever element it is that we're looking at. Now, when we knock out an electron, remember what we're forming is a cation. So that's why we get X plus, and we get E minus on the product side. Remember, this is not a beta decay that we talked about with nuclear chemistry. We're talking about knocking out an electron from an atom. So don't confuse this with nuclear decay. Now, think a second and look at what we're talking about. We have an element becoming a cation plus an electron. What principle have we looked at very, very, very recently that this sounds suspiciously like? Well, think a second here. If you need to, pause, but I'm just going to give it away. It's ionizing ionization energy. So really this equation is very similar to our ionization energy equation. We're just looking at putting on the reactant side the amount of energy needed to basically knock out our electron. And it's not like ionization energy in that we're talking about the energy needed to pull out the next electron in the atom. We're talking about the energy involved in knocking any electron out of an atom and what its resulting kinetic energy is. Why that's important, we're going to look at here. Now, keep in mind we have energy in the form of a photon coming into our element. And law of conservation of energy, that energy has to go somewhere. Well, one place that energy goes is to basically break apart our electron from the protons in the nucleus. So those electrons are bound to the nucleus, so we refer to this as binding energy, and don't confuse this with nuclear binding energy. Similar idea applied in a different application here. So we're talking about the binding energy of the electron measured in joules. Sometimes it can also be measured in other units as well. Kilojoules, megajoules, electron volts, all those are different ways of measuring energy. Now, what you're really overcoming to pull out that electron. The binding energy you're referring to is really a Coulomb's law application. Remember, distance kills attractive forces, one of the things we talk about with Coulomb's law. And the greater the distance from the nucleus, the less that nucleus is going to hold on to those electrons, the easier it will be to pull out the electron. On the flip side, the closer we are to the nucleus, and this is a core idea to what's happening in PES, the closer we are to the nucleus by Coulomb's law, strengthens the attractions, which means it's going to take more energy to overcome that binding energy. And remember, binding energy is then related to ionization energy. It's not the exact same thing, because in ionization energy, we're looking at the exact amount of energy needed to remove the next electron from the atom. But we are talking about removing an electron from the atom to make a cation. So it is in some ways very, very, very similar to what we talked about with ionization energy. Now, here is the key to what that detector does. So part of our energy is going to basically be spent in breaking the binding energy, but there's going to be leftover energy. That energy can't be destroyed. The atom absorbed that energy. The energy has to go somewhere. Well, where the energy goes is in that photoelectron. The extra energy becomes kinetic energy in our photoelectron. And this is really what our PES detector is measuring, this right here. Now we know, based upon the frequency and energy of the type of radiation we're using coming in, we know the energy of the photon hitting our element, and we can measure the kinetic energy of the photoelectron that comes out. From that, we can calculate our binding energy, or what we can also call our ionization energy. So that's really what we're looking at when we look at the data for binding energies on the PES spectrum we'll look at in a second here, is we're looking at the binding energies of the different electrons inside that atom. Now, here's an example of a simplified spectrum. Now, the reason it's simplified, you have to pause a second and think here. Now, inside a fluorine atom, so look at your periodic table, fluorine would be how many total electrons and where are those electrons at. So take a quick look at your periodic table and look at where all the electrons in fluorine are. Well, we've got 1s electrons, and we've got 2s electrons, and we have 2p electrons. Now, if you really think about some of the processes with attraction and repulsion, some of the different forces we've looked at, it would make sense that even for a 1s situation, that when you take out that first electron, it's going to be a little bit different in energy than when you take out the second electron. So let's say we have a helium atom and we're stripping out our first electron. Well, remember, there's some electron-electron repulsion that exists in helium that does not exist in hydrogen, or when we only have one electron left. So that first electron out is probably a little bit easier, lower in binding energy than that second electron out, even inside the exact same orbital on the exact same sublevel. So what we really get is information that needs to be cleaned up a little bit, because instead of one peak for that 1s situation, we're probably going to get two peaks that are close to each other but not the exact same. And then in P's, you're going to get kind of a similar thing occurring. And those variances, the splitting that we're talking about here, is going to be even more exaggerated sometimes with those sublevels and so on. So really what happens is we have to clean up the image that comes out. And that's what is meant by the simplified PES spectrum here, is we take all of those energies that are very similar, that really are talking about the same exact sublevel, and we put them together in one diagram. So that's what I mean by a simplified PES spectrum. Now, a couple things that you should understand about this spectrum you're looking at. First, let's take a quick look at the x-axis. The x-axis in this case is energy. So it stands for our binding energy. Now, it's kind of a goofy axis because if you notice, it starts out 0 to 10 on this first level, and then it ends up going from 10 to 100 on the second level. So we have two different x-axes and two different scales on the same x-axis here. Now we do that because if we were to graph this on one line, I mean, take a look at our relative numbers here. 1.68, 3.88. We want to see some differentiation between those two. And then next we have to graph 67.2. Well, our graph stops at 10 here. 67.2 would be way off scale. And if we tried to put it on scale, that would cause these two to scrunch together, and it would be very hard to see sometimes the difference between them. So what they've done is they've split our axes here. So that's why we've got two different x-axes. That way it's easier to see. And notice they're telling us the energy anyway, so we can see the relative energy between them. So that's what our x-axis represents, is the binding energy of some different electrons. So that's the first thing. Second question, what does each peak represent? Well, when you take a look at your peak here, you have to think about, remember I said this was fluorine, and fluorine is 1s2, 2s2, 2p5. Now think about the ideas trying to remove these electrons. Now, the 1s electrons are going to be very close to the nucleus. By Coulomb's law, then, they should have significantly higher binding energies than the rest of the electrons in here. So which one is our highest? Well, that's this one right here. So 1s is what that peak should represent. And notice it's a height of 2. Now, the next highest in binding energy is probably going to be our 2s here. So this would be our next highest. So that's probably 2s. Notice, height of 2. And then finally, our easiest electrons to remove, the lowest binding energy, would be our 2p sublevel. Well, that must mean this is 2p, and notice it's 5 high. So what does each peak actually represent? Well, the peak represents the sublevels. And remember, this goes in opposite order. When we talk about alpha, we always start with 1s. Well, here we're ending with 1s, so to speak, in terms of our binding energy. And then what's on the y-axis? Well, that's the relative numbers of electrons. Well, notice if that's the 1s and that's the 2s and that's the 2p, and it's 2 high, 2 high, 5 high, that looks suspiciously like the number of electrons we have in each sublevel. So X represents the binding energy, and Y would represent how many electrons are at that binding energy compared to the other, or relative to the other. So what does the height of the peak represent then? Well, it represents how many total electrons. Now, this peak that is too high here would be twice as high as if we had a peak that was only 1 high. So really this 5, 2, and 2 would be relative to what would 1 electron have a peak of. So in this particular case, what's happening is that 5 is 2.5 times bigger than the other peaks. Well, each of the other peaks represent 2 electrons. So 2.5 times 2, that's got to be 5. So that's how we can establish the scale here. So that idea is what's going to be coming into play in every single graph you look at. Now, one thing to pay attention to, though, is be careful, because I have seen images online where these are flipped and binding energy is on the y-axis and the relative number of electrons is on the x-axis. But this seems to be more consistent with what I've seen with different graphs. Now, I mentioned briefly hydrogen and helium. So what would they look like? Well, here is hydrogen, the top one. And that would be the 1s, because that's the only thing we've got in there, and it's got 1 electron in it. So this is our 1s1 electron peak. And notice that has a binding energy of 1.31. Now when we go to helium, we have 2 electrons. And here is basically our helium peak at 2.37 for binding energy. Why is this peak higher? Well, think about it. We've got 2 electrons in helium and only 1 electron in hydrogen. So relative to the other peak, we would expect it to be twice as high. Now, second question, why is it farther to the right? That one may be a little less obvious. So how come in this particular case, the peak is farther off to the right? Well, think about the differences between hydrogen and helium. Helium has 2 protons in it. That's a stronger nucleus. Now, both of these electrons are in the 1s, our valence level. And remember, valence electrons aren't as good at screening each other. So while that second electron in helium does do some screening, by and large, it's twice as strong of a nucleus. We should expect it to be the neighborhood of twice as big, with a little bit less because of the screening that does occur and the electron-electron repulsions that help us pull out that electron just a little bit. And sure enough, that's exactly what we see. It is not quite twice as big. So that's why the peak is farther to the right. It makes sense based upon the strength of the nucleus and effective nuclear strength. Next graph that we're going to look at here, notice it's unlabeled. So we're going to go through and do some work with this that you need to be able to understand. First off, what element is this? Well, how would I figure out what the element is? Well, remember, elements are, what element we've got is determined by the number of protons, its atomic number. In a neutral atom, protons equals electrons. And what's on our y-axis over here, but a relative number of electrons. Well, it looks like this one is too high, and this one is too high, and this is 1, 2, 3, 4, 5 high. Well, what substance has 5 electrons? Plus 2 electrons for a total of 9. Back to fluorine, one I think we'd mentioned before. So element here, this must be fluorine. All we really have to do is count the relative heights of the peak. Second question, labeling the peaks. Well, I've actually started the process. And remember when we were talking about on the previous slide, by Coulomb's law, the sublevel that is closest to, and remember each one of these peaks represents a sublevel. The peak that is closest to the nucleus is one that's going to be the absolute hardest to pull electrons out of through Coulomb's law. That would be the one that is highest in energy, which in this case is the one that's far off to the right here. So this must be our 1s peak, and it's too high. So that's our 1s2 peak. Now, next inside the fluorine atom is our 2s. And that's also too high, so that's 2s2. And then finally in fluorine, last comes our 2p sublevel. So that would be the easiest to remove electrons, so it'd have the lowest binding energy. So this has got to be our 2p5 peak. So remember, you start at the highest, way over here at the very highest, and then you work through off-bow. One of the things that PES does for us so well is it shows us valid information, especially in the simplified graph form here, to really look closely at what we know is true or what we believe to be true about our electron configurations. We can support much of the stuff that we've talked about with electron configurations with PES, and that's its strength. Now, why is the 1s peak farther to the right? Well, we've already talked about that, so think about the discussion. Farther to the right means higher in energy. Well, what's going to be the hardest to pull out? Our 1s. So 1s has got to be the very highest in energy every single time. And be careful when they're multi-levels. So look closely at the particular x-axis you're studying. Why is there a bigger gap between the 1s and the 2s than there is between the 2s and the 2p? So basically, how come this gap is so much bigger than that gap is? Well, once again, apply the concepts that we understand and know, and we've been talking about time and time and time again. Force of attraction, force of repulsion, how distance can affect those things, and so on. Well, think about the difference here. In this particular case, we're looking at a difference in first energy level to second energy level with the green gap here. Well, that's a whole nother energy level. And remember, when we drop an energy level, we're getting significantly closer to the nucleus. And by Coulomb's law, it should be significantly harder to pull out electrons. So we would expect our second level information and our first level information to be very different in energy based upon the different value of n in Coulomb's law and distance from the nucleus. So it makes sense that that difference should be the bigger one. And the difference between the 2s and the 2p is going to be a significantly smaller difference in energy than between the 1s and the 2s, because there we're talking about the same value of n. Next, one often very useful thing to do is lay two different graphs on top of each other so we can see the differences between the two. So here what we're going to do is look at the differences between fluorine and nitrogen. Now, one of the things I want you to notice is the blue, which is our fluorine, is always shifted to the right in our 1s situation, our 2s situation, and our 2p situation. Well, does that make any sense? Well, yeah, think about it. Remember, we're looking at two things that are in the same period on the periodic table. And remember, every single time you see the same period, you should be thinking effective nuclear strength. And fluorine is higher in effective nuclear strength. So at all of its levels, you would expect fluorine to be better at holding on to electrons. So therefore, you would expect the binding energies of our fluorine to be larger than the binding energies of our nitrogen. Now, exceptions to the octet rule, which we have taken out in large part in AP chemistry, but we still discuss them from a regular chemistry point of view, those will end up being shown on here as well. So something like copper and something like chromium, which we talked about in your notes, when you look at their spectrums, they will uphold the fact that those actually are exceptions to the octet rule. And remember that when you're doing your homework. But it would make sense here that fluorine peaks would be farther to the right than your nitrogen peaks. Now, when you're going to look at the homework, I want you to remember a few fundamental things. Remember, everything we've been talking about is dealing with how proton-electron interactions affect the attractive force, how electron and electron interactions affect attractions, how effective nuclear charge affects attractions, and how N affects attractions. All these are things that I've discussed or mentioned not only in this video, but in all the other discussions we've had related to these. So when you get to the toughest one on the homework, the very last one, think about explaining why that one peak is displaced just a little bit from where it should be. And filter it through these ideas, and it'll make it much easier to understand why it's doing something a little bit differently. So take a look at its orbital diagram for its highest sublevel, the sublevel that we're looking at here, and see what's going on different between the two, and that should help you. Well, hopefully this makes PES spectroscopy make a little bit more sense. Thank you for listening.